Okay, I think we're live. Hello, hello, hello world. So, welcome back. Okay, so the last problem we were looking at yesterday really caught me, man. Caught me by the got me by what? By the outer reaches of my understandings. This was nowhere on my periphery. I mean, I had no idea what they were talking about here. Okay. So these things they're describing are called Kmaps, and Kmaps are pretty cool, actually. But basically, to explain it in simple terms, you get this. I'll try to explain it quickly. Basically, you've got this. You've got this square. It's not quite a square. All right. So you got this square that's not quite a square, right? And we're gonna draw it like this: A, B, C, D. And we're gonna say 0, 0, 0, 1, 1, 1, 1, 0. And we're gonna repeat that on the other side. You might be wondering, what the heck are we looking at here? And I will explain. I shall explain. Okay. That's not a D, is it? That don't look like a D. Alright. So what the deal is with this is there's a couple things to note. So first things first, there's this thing called Graycode that you got to understand, which is involved. And the idea behind Graycode is if you have, let's just take 3 like so. So this is sort of normal binary. What your normal binary is going to look like. 1, 2, 3, 4, 1, 2, 3, 4, right? This is sort of what your normal binary code looks like. I realize it's a little sloppy here, but did it quickly as you saw. The thing you notice is that from here to here, there are 3 changes in bits, right? And the issue is actually a mechanical one. A lot of the stuff is like karnaugh maps and Graycode and things of that nature are actually things that were invented with regard to hardware way back when. Like we're talking like many years ago. People were still kind of learning about. I don't know exactly what time we want to pin it at, but let's just say they were working a lot with actually mechanical devices that would sort of represent computation or logic or moving bits, changing bits. They still were really dealing with a lot of sort of mechanical constraints and mechanical things. So one thing being, if you wanted to switch from this state to this state, you'd have to have something that can handle 3 different bits changing at the same time. Whereas if you wanted to move between states in something called Graycode, that's what's referred to as, the advantage of Graycode was that every transition would be exactly 1 bit difference. And so Graycode would be, you actually shift the way you can do sort of the typical Graycode, or not typical Graycode, but the Graycode I was looking at. What you do is you see how this alternates 1 1 0 1 0 1 0 1, and this alternates 0 0 1 1 0 0 1 1, and then 4 zeros 1 4 1s. Graycode, what you do is you say, okay, we're gonna have alternating blocks of 2, and we're going to shift our block initially. So it'll look like this. 1, 2, 3, 4, 5, 6, 7, 8. Right? And now you shift. So this is a block of 2. Now you're going to have a block of 4 that's shifted down 2. Right? And now you're going to have a block of 8 that's shifted down 4. And obviously there's a cutoff here. Right? We don't have the block. We have a block of 1 at the bottom and a block of 2 at the bottom instead of a block of 4. And then we don't even have a block of 8. We just have a block of 4. That gives you a nice the pattern for Graycode. And what you'll notice also is 1 bit shift. 1 bit shift here, 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 and 1 bit shift there. So, very nice. Each transition only requires 1 bit shift. So that's what's going on here. You might be wondering what the heck, why is it 0, 1, 3, 2? It's because it's 1 bit shift here, 1 bit shift here, and then 1 bit shift here. And in fact, if you perform this as shown, every single one of these transitions will end up being 1 bit shift to the other, all the way across. Which is kind of unusual, kind of interesting, kind of unusual. Or at least not something you would typically think of. By the way, what this is this is CD. These are sort of the truth tables, A, B, C, and D, truth values. These will be 0, 0, so C is 0, D is 0. You know, A is 0, B is 1, A is 1, B is 0, right? So now the picture that they're showing over here, and this is pretty interesting, is what you can do. So the idea is, okay, there's bit shifts sort of between each of these states, but there's also bit shifts this way, right? You could bit shift that way in one bit shift. You could also bit shift this way, and in one direction, bit shift this way. And the way, so this is going to be, we're going to have build a Karnaugh map. What's interesting is you end up with these sort of, we'll do something like this. Basically, what you do with the Karnaugh maps, there's this thing called, there's like a lot of concepts involved in all this, but there's this thing called the canonical disjunctive normal form or the canonical conjunctive normal form. So what those refer to, I believe they are basically groups of things that are ANDed, and the groups are then ORed, or vice versa. They're groups of things that are ORed with each other, and then they are ANDed afterwards. So they are typically represented as, so if this is A, B, C, D, you could have A plus B plus C plus D, or you could have like A plus B times C plus D. And the idea is this is a sum of products, and this is a product of sums. And the reasoning behind this, the rationale is, and you can think about it this way, if you're thinking about it logically, adding zeros and ones together is a lot like taking the logical OR of those operations, and multiplying to zeros and ones is a lot like taking an AND over values, right? So if you have zeros and ones and you multiply them across, if there's any of those are 0, the whole thing's a 0, like an AND would be 0. And only way to get a 1 is if everything is a 1. And adding zeros and ones, also, if everything is a 0, that's the only time you get 0. And if any of those things are a 1, then you end up with a 1. The same way that an OR would work, which is really interesting. That went over my head initially, but I finally understood that after like kind of processing that for a while. So the sum of products refers to taking an OR over a whole bunch of ANDed things, right? Products multiplied together. And then the product of sums is you take a whole bunch of sums and then you multiply them across. And finally, what's interesting about Karnaugh maps is that this sum of products and this product of sums actually has an analog to these maps where you can gather the zeros into different pieces. So you can do like this kind of a deal. Actually, you'd want to do it this way. This is one approach. And you can find there's a logical kind of meaning to these different pieces. I'll show you what that means in a moment. Or you can use so I think this will give you is it product of sums? I don't remember. I'll go through it in a second, we'll find out. Yeah, no, this is the product of sums are the zeros, and the sum of products are the ones. And I'll show you what this ends up looking like. It's very interesting. So I just kind of randomly, by the way, this coincides with the following 16. So there's 4 bits we're looking at. So there's 2 to the 16th, there's 2 to the 4th, there's 16 different sort of truth values. This would be here. We'll just map them all out. And we won't do it in Graycode. We'll just do it in regular binary form because it's a little easier for me to process. So I don't use the Graycode too often. By the way, then there's like these kind of recursive algorithms, I guess you can do with respect to not recursive, but yeah, I guess recursive algorithms you can perform with respect to these generating the binary values. All right, so okay, and then now we'll give you the truth values according to so 0, 0, 0 we have 1, 0, 0, 0, 1 we have 1, no, we have 0, 16 of these things. I just kind of picked a bunch in this map, but we can give you the actual binary function. 0, 0, 0, 1, 0, 0, 1, 1 is 0, 0, 0, 1, 0 is 1, 0, 1, 0, 0 is 0, 0, 1, 0, 1 is 0, 0, 1, 0, 1 is 0, 0, 1, 1, 1 is 0, 0, 1, 1, 0 is 0, 1, 1, 0, 0 is 1, 1, 1, 0, 1 is 1, all the 1 1s in front are 1s, 1, 0, 0, 0 is 1, 1, 0, 0, 1 is 0, and finally 1, 0, 1, 1 is 0. And we said 1, 0, 1, 0 is 1. Okay. So there you go. This is what the actual, let me save this also as karnaugh maps. So the thing to note about is, so this is what a sort of a binary function would look like, right? It's got, you know, four inputs in this instance, each of those being a variable 0, 1, true or false, and the binary mapping is going to give you the binary Boolean mapping will give you either 0 or 1 depending on the inputs, right? That's sort of just like a, not a binary relation, but a Boolean algebra kind of function, I guess. Now, there's a few things to note here. The first thing is note that these are sort of connected to each other across multiple, what do you call that? It's sort of like a cyclical kind of a way where, you know, it wraps back around, right? And the reason, and that actually is related to this torus here. That's what they're describing. They actually took this function, mapped it to Graycode, which is this sort of sequence, and then curled that sequence around to create a cylinder, a torus rather, which somewhere around here says the word toroidal, which I thought was a very interesting word. Toroidal. Yeah, toroidally connected grid. Now, how about that? But that's what this is referring to. This little pictograph here. It's you can curl this around in a circle and then curl around again. And this is how these things are considered, right? They're sort of considered connected to each other. These pieces, they wrap around, touch each other. Anyway, so that's really cool. And the idea is you take, so to get this sum of products, right? What we're going to do is say we're going to look at all the ones. We're going to have groups of ones, and what's going to happen is it's going to be the sum. So we're going to OR these groups of ones. So when any of these ones are hold, any of these cases hold, then this entire circuit can be just, but basically all of those different pieces can be ORed. So you're going to collect these pieces and OR them together, and you get this sum of products. Now each of those pieces are the products. Now what ends up happening is you say, okay, for this green portion, right, straight across, this AB doesn't change at all. Or rather, yeah, AB doesn't change, but CD, it could be anything, and you'll always get 1. So you could say this is AB. So for this one, SOP, you're going to have A, B. So if you have A and B, right, then it doesn't matter what you get for C or D, and that'll get you true. And then you're going to OR this other one, which is the 4 that are sort of 4 corners that are connected to each other. These are, you say, AB is 0, 0, CD is 0, 0. AB doesn't change from here to here. So wait, so C, this is interesting. This could be, C could be 0 or 1. Now how does this work? What do you get here for this? This is definitely an interesting one. This is like 0, 0, 0, 0 is a 1. 0, 0, 1, 0 is a 1. 1, 0, 0, 0 is a 1. And then 1, 0, 1, 0 is a 1. Now, what doesn't change between all 4 of these? Now, I could be wrong about this. Maybe this doesn't quite work the way that I think it does, in that all 4 of these are connected to each other. I realize these are connected to each other, and these are connected to each other. No, maybe this is exactly what I want. I'm actually not sure. I'm a little conflicted here. Well, you could say you don't care what A is, right? In any of these cases. B has got to be 0 though. In all 4 of these cases, B is 0. A could be 0 or 1. C could be 0 or 1. But D has got to be 0. Yeah, that's what you want. Okay. So A is 0 and D is 0. So this is a negation, by the way. There's a few ways to write the complement, but that's one of them. Just a bar over the top. So no, sorry. B is 0. A little confusing, but A in all 4 cases, it's sometimes 0, sometimes 1. B in all 1, 2, 3, 4 cases is a 0. C in all 4 cases, it's 0 or 1, but D in all 4 cases is a 0. So you're going to have D is 0, B is 0. So this is the sum of products you end up with, right? Because that covers all the ones. Alternatively, you can take the product of sums, right? So this could be modeled with an AND gate over these 2 pieces, and an OR gate of all those components of what's left over, right? The product of sums, on the other hand, you would have. So I think I got some kind of message. I don't know. All right. Spam with stuff from YouTube, man. The product of sums now is actually sort of a negation of all of that. So you're actually going to look at these zeros. When are you going to get 0, or when are you going to get false? And you say, okay, there are these two cases, right? These four, this one, and obviously this wraps around as well. So this case is, it looks like 0 changes, right? Or C changes. So D is 1 in all 4 of these cases, and B is 0 in all 4 of these cases. So B is 0 and D is 1. So B is 0, D is 1, B is 0, B is 0, D is 1. Now, because B is 0, we're going to take the complement, B is going to be 1. Because D is 1, we're going to take the complement, B is 0. Right, that's how it works with the. That's how you sort of do this logical abstraction with regard to the product of sums. You actually take the negation of these things, and now this is one of the first product, and the second product is going to be this other piece here, where you have 0, 1, and it doesn't matter what else there is. So A is 0, B is 1, A is 0. B is 1, the 1's become negated. And the rationale for this, the reasoning, is that you're trying to get these zeros, so it's actually, you've actually got to negate. Like, how does it work? It's, these would give you, if you use these logical constructors, would give you 1's. Is that right? Actually, I'm not really sure. It has something to do with De Morgan's law, where you're gonna double negate. So you can double negate this and end up with this, and double negate this and get up with this. So there's one negation that happens by considering the zeros. The other negation happens by actually just negating the values you're considering. And the mechanics of it, De Morgan's law swaps between products and sums. It swaps conjunctions and disjunctions when you apply it. So the double negation actually gives you sort of this swapping thing that goes on, which is kind of neat. But yeah, that gives you your product of sums. This is the canonical conjunctive form, right? Because you're conjoining these disjunctions. And this is the canonical disjunctive form, because you're disjoining conjunctions. Really interesting. I was super confused by all of this when I was reading about it. Now I finally got like a picture of it that sort of makes sense. But really interesting. What this stuff is karnaugh maps. So the whole idea behind all this, and there's a lot of pieces to this, as you notice, right? There's Graycode, there's conjunctive, canonical conjunctive normal form and canonical disjunctive normal form. There's the toroidal connection. There's what else? There's De Morgan's laws. There's this notion of there's this sum of products versus product of sums. There's this analog between, or analogy between summation and products, and the conjunction and disjunction, logical conjunction, logical disjunction. There are all these pieces, there are all these pieces. None of it particularly complicated or difficult. Kind of complicated and difficult if you just try to look at it like on the surface. But if you take a moment to kind of let it sink in and process it, it actually is not too bad after all. And all of this, the reasoning for it is you want to simplify this Boolean function. Instead of trying to give this whole mapping as it is to somebody and say, okay, go create a circuit that does this. What you want to do is reduce this to one of the simpler forms in the canonical, or one of the canonical forms, and then you can decide between using. I guess this would use one. It would use one inversion, two inversions, 2 OR gates, and then 1 AND gate at the end. And then this would use also 2 inversions, and 2 AND gates, and then 1 OR gate, right? So this I actually think would probably use less. I don't know, one AND gate at the end here. So actually, it seems like they both use the same number of gates that you need in your circuit. So that's kind of interesting. Yeah, karnaugh maps. So now the question that we were looking at, while this is all well and good and very interesting. Oh yeah, by the way, the one thing to note is that you group, in order to get the sort of minimal form, you group as many elements as you can together, and you consider the components that don't change, right? So here, right, we got 4 components, and then here you got another 4 components, right? And actually, I kind of created this in such a way where I sort of already knew that you're going to break it up nicely into pieces of 4, groups of 4. But you could do whatever. I mean, it could be a group of 4 here, you know, on the sides, and then maybe just a 1 in the middle, and then maybe a 2 on the side. As long as your groups can be can overlap, even if needed, although they must be totally contained by either zeros or ones, depending on which form you're going for. So if your sum of products, it has to be all ones, and it has to be some power of 2. Excuse me. It could be vertical, horizontal, could be rectangular even, but it's got to be a power of 2, whatever it is that you select, and it's in such a way that you can sort of eliminate one of these variables, because that's really what you're going for, is you're trying to eliminate as many variables as you can, as broadly as you can, to get the simplified version of this function. And finally, you can also do another thing, which is, right, if you have a single 1 that's just sort of by its lonesome, then that actually just, you add that, and that you don't get rid of any of these values. You just end up with, you know, obviously this sum of products would be otherwise 16 different sums of all the ones, or not really the 16. It wouldn't be 16. It would be of all the ones that, all the things that are ones would be added together, and then obviously you can logically deduce that, you know, oh, okay, for whatever value of C I get, if I have A and B, then it doesn't matter the values of C and D, and then, oh, if I have not B and not D, then it doesn't matter what the values of C or A are, and that whole logical conjunction reduces to something a lot simpler. So that's very interesting. That's the idea. Now, as you could tell, what you're looking for, really, it's sort of a clever way of figuring out how you can group the ones in such a way where you can notice pieces that don't change, whereas everything else does change across that group. Right? That's also, by the way, why it needs to be a power of 2, is because only powers of 2 will contain all of the bits required. Right? This is 2 to the 4th, it's 2 squared. 4, this contains all of the bits in a sort of a stretch, where if everything else is consistent across that stretch and you have all ones, then you can easily reduce this to just one portion, one subset of the truth table, which is really cool. But it's a very clever way of doing that, right? In a way that's sort of visual. That's the whole idea behind karnaugh maps. So obviously, for the problem we're looking to solve, kind of had to go through all that work to figure out what the heck we're dealing with, and you realize, oh, you could process this in kind of in a not efficient way, but a simple way. That would be, all right, you're just going to look for all of these cases where you have you have results true on the inputs, and then all of the inputs for a given sort of where the inputs the amount is a power of 2, and for those inputs, and the corresponding inputs to give you those results share some consistency across those values, right? So it's kind of interesting. I haven't fully formulated the algorithm that I want to use, but I'm thinking some kind of brute force algorithm can do the trick. You basically would be the equivalent would be of just looking at every possible sort of sequence of 4 that you could have, of which there are, there's a few, right? Every sequence of 16, which is the whole thing, then every sequence of 8, which there's only so many of them, every sequence of 4, right? Every sequence of 2, and then every 1. And what you do is you kind of perform like a what do they call that? Kind of the way that you would, if you needed to make change, you would start with the biggest values and remove those, and then use the biggest coins, then use progressively smaller coins. You sort of process the largest pieces first, and that'll sort of guarantee you the sort of a minimal result. By the way, the minimal result is by no means unique. So that's actually what this problem is asking for. But by the way, we can go back to the problem and describe, and understand now what we're looking at. There's one more thing here, which is, yeah, I think the algorithm I want to use. See, the tricky thing is, excuse me. Basically, there's a whole bunch of different pieces. What you'd want to say is like, okay, there's only one way to choose 4 out of 4, right? And that means that basically is saying that all 4 don't matter, right? It'll always have true no matter what selection you pick. That's this case, right? The whole thing. That's all 4. Then there's 4 choose 3 ways such that one variable doesn't matter, right? So there's 4 different cases to check there for those one variable doesn't matter, right? And then so there's 2 to the end of these, right? It's 4 choose 4 plus 4 choose 3 plus 4 choose 2 plus 4 choose 1 plus 4 choose 0, and 4 choose 0 where everything matters is there's only one of those also, and that would be. Now that's kind of interesting, that one. I'm not really sure what to think of that. When everything matters. There's 16 different cases there, though. Like there's 16 different possible, whatever you want to call these things. So I'm not sure if I'm getting it totally correct when I think of it that way. Also, suddenly just everything got really kind of bright. Let me think about that. 4 choose 0. All 4 don't matter. That's the whole thing. When only one element doesn't matter. There's a lot of different combinations, though, for those things, I suppose. Like, when only one thing doesn't matter, there's 4 different ways for that to happen, and then each of those 4 ways contains 4. No, it's actually 2. Let me think about that. If only one thing. If all 4 things don't matter, then everything's true. There's only one way that can happen. If only one thing, if only three things matter, or one thing doesn't matter, all four things don't matter. If three things don't matter, right? There's really it's only 0 or 1 for the thing that does matter. It's one variable, but it has two different cases, and you've got to check. Well, it's a grouping, right? So there's two different groupings over the 16 values, 16, yeah, truth functions, whatever you want to call it, 16 truth possibilities. 16 possibilities, right? There's two groupings of the 16 possibilities. And then there's, if nothing matters, if all four of them don't matter, then you've just got one grouping to look at. If three things don't matter, then you've got two groupings per truth value to consider. So that means there's 8 different groupings to look at, because there's, for instance, if it's A is the only one that matters, then you're looking at a grouping of all ones for the other 8 possibilities are all 1. And the only thing that changes is A. And then you could do it the other way around, where for those 8 possibilities, no, I'm sorry, hold on, this is thinking about it incorrectly. The things that don't change are the ones that matter. Yeah. So the ones that don't. So for all 4, everything being true, nothing matters, it's just empty. For something that only A is the thing that's changing, but you cover all the other possibilities, although A is differs between those different possibilities. Or excuse me, A doesn't change between those possibilities, right? So then you could, two groupings would be either A or not A, right? Those are 2 different groupings, and then you have that same thing for all 4 variables, right? A, B, C, and D. So you actually have 4 times 2 raised to the, well, 4 choose 3 different ways to check on these things, and then each of those have 2 different groupings. So there's 8 different groupings. Now if you look at when 2 things don't matter, you end up with 4 choose 2 different ways that this could happen, that you could select these 2 variables that matter and or don't matter. Right, so 2 of them don't matter, 2 of them matter. 4 choose 2 is what? What's that? 12 by 24 over 2, 12, 6 different ways to think about this, 6 different possible combinations of these variables. And then each of those variables have 2 squared different possible ways to combine them as well. So you end up with 6 by 24. 6 by 4 was 24. Different groupings to consider. And then you end up back at 4 choose 1 again, 4 different ways, where, what do we say, if all 4 don't matter, then 3 of them don't matter, so 1 matters, then 2 matter, and now we're saying 3 matter, and 1 doesn't matter. There's 4 different ways to select that one that doesn't matter. But there's 2 cubed ways where these ones that do matter can be combined and grouped. So you end up with 8 by 8 by 4, it's 32 different groupings to consider. And finally, we get back to the case which I was thinking of, where I was like, wait a minute, what happens if you have just ones kind of scattered all over the place? There's a whole lot of these groupings to think about, to consider. And then it dawned on me that, yes, there's Now all the variables matter, right? For choose 0, different ways to do that. And because there's each of them could take on a different value, there's 2 to the 4th of those. So it's 2 to the 4th times 1 different groupings to consider. So you have 2 to the 4th times 4 choose 0 plus, or really it looks like this. It's, plus 2 cubed 4 choose 1 plus 2 squared 4 choose 2 plus 2 to the 1st 4 choose 3 plus 2 to the 0 4 choose 4, which then these are the different groupings to consider, which could be rewritten as the summation of I equals 0 of 4 choose I times 2 raised to some function of I, which is, I will call this, instead of, you can kind of see why I'm doing this, where I'm going with this here. Hopefully you can see it. I'll call this n. We'll say n minus I times n choose I. Which, by the way, you could just as easily reverse these things and say, go the other way around, which is just I, right? Because you could just 4 choose 4 here, 4 choose 3, etc. Right? The sort of definition of what do they call this? Combinatorial calculations. I don't know what the name of this thing is. By definition, this construct is symmetric across. It's palindromic in terms of the numbers. This is a few ways to understand this. This is also not the Sierpinski triangle, but the other triangle is another triangle. Pascal's triangles. Right, every row of Pascal's triangle is palindromic, and these values represent the sort of the row of the 4th row of the or actually it's the 5th row of the Pascal's triangle. These are also, there's a name for these things. They are, there's a name for it. What's it called? What is it called? It's selection without replacement. Is that what it is? It's kind of a name. Sorry. Got a text message. So, yeah, I forget what this is called. It's selection without replacement. It's not permutation with it. It's not just selection without replacement, though. It's selection without repetition and without replacement. I think that's what it is. I forget what there's a name for it. Special kind of replacement. Okay. What is this called? What is this called? And choose k meaning. It's called the binomial coefficient, and it's also Pascal's triangle, we already got that. Factorial, we got that. Pascal's triangle. Oh, there's something here, Catalan numbers. It's kind of cool. Logarithmic differentiation. Interesting. There's something special about this though, which is, oh yes, what I was talking about before. This is what our sum is. The formula is. We can rewrite this as described. Actually, I didn't know that this is the case. Sums of binomial coefficients. Maybe I should have known that. Oh no, this is, oh yeah, no it is, right? I times n to the I. No, this is not. This is actually a lot more expensive than that. The Van de Monde identity, hockey stick identity, Fibonacci's. That's kind of cool. Multi-sections. Partial sums. I'm looking for and choose an unordered subset. That's what it is. It's unordered without repetition. Yes. Or alternatively ordered with repetition. It's kind of weird to think about it ordered or unordered because it's like 1, 2 or 2, 1, right? 2, 1 is sort of ordered as a different order than 1, 2. So if you say there is an order involved, then you end up with more than 1. You end up with a different, like all the different permutations. Whereas if you say it's unordered, then you basically impose an order, which is, and just take that one, all of the ones that have the same order correspond to the same. That's also, by the way, where you get this formula from, the factorial formula. Like if you have it, n choose I is n factorial over I factorial, n minus I factorial. The reason that you end up with, so the n factorial is all the permutations, but then you only want permutations of the n minus I elements, like the I elements. So you divide by these n minus I portion in order to not, in other words, you only want to select the first three boxes, let's say. So then you do n, if I is 3, then normally you'd have sort of n factorial for all the permutations, and then you divide by this n minus I factorial to lop off the rest. And so you get all these permutations, but then you want the unordered permutations, and so each of those 3 elements, there's 3 factorial ways to permute those with amongst each other, and you're going to say all of those are equivalent to the same one, so you would divide by that I factorial to bring you to one of these. So instead of having, 3, 2, 1, 1, 2, 3, 3, 1, 2, etc., you take all those permutations and you go to 1. So you'd have x times k gives you 1, where, sorry, if you allowed permutations, you would end up multiplying by I factorial, right? So allowing, so x times I factorial gives you this sort of y. That means that x is going to be y over I factorial. Yeah, what you want times all these permutations gives you what you've got, which is this thing, right? Which is to say that this is n factorial over n minus I factorial. That implies that you should divide by I factorial. Yeah, it's kind of a tricky, nifty thing, but that's the basic explanation for like how you can derive this formula, sort of logically. Why you get that formula? It's pretty cool. It's kind of cool. But anyway, yeah. So those are binomial coefficients. So this is like a super. This is basically dominated by something that's exponential. It could even be like super exponential, because this sort of is exponential as well. The only reason why I don't think it is because you could do like n choose like something n over 2. If you do n choose n over 2 and 2 raised to n over 2, you end up with 2 raised to n over 2 times n over 2 factorial over n over 2 factorial squared. I don't know. Which I don't actually know what the dominant term is in this case. Like maybe this is just dominated by n factorial. It's definitely at least bounded above by n factorial, but it's basically expensive. Sort of the bottom line. I don't think it's dominated by n factorial, but it's pretty big. This is pretty big. This is going to be the brute force solution that we employ to solve this. That's basically what they're asking for. Is they're asking to take. It doesn't have to be this algorithm, but an algorithm that will resolve what I described. These karnaugh graphs, or karnaugh, these different possibilities, and these are all the different groupings that we'll end up looping through if we loop through them exhaustively, which is fine. I think it's okay. I think it's doable. It's definitely expensive. I think it's bounded by. I think it's ultimately bounded by this. What do they call that term? This exponential term. I think it's ultimately bounded by this I think it's ultimately bounded by this exponential term. I don't think there's any way around that. Yeah, I don't know if it's completely bounded though. That's I'm kind of conflicted. I'm not really sure. I don't know if that's the absolute bound, the correct bound. It probably is, especially given what we were just looking at. That was describing like different functions of binomial coefficients, different summations. Anyway, so I mean, yeah, that's all well and good. What do we think of? What do we consider now? What do we do? So yeah, let's just ponder this some more. So we'll be right back. I'll take a break in a moment. I'll take care of something quickly. Exponential, certainly. What are we missing? Something's missing here. I think I covered it. No, I think I covered all what I wanted to say. The bottom line is you want to, what we can do is loop through, brute force all these different groupings. So what they're saying here is that they're describing this function by saying, given these truth values, which is false, true, true, false, right, for A, B, C, and D. Given this set of truth values, which is going to be, it's actually, they call it the conjunctive form. So, or rather the disjunctive form of conjunctions. They describe it here. The inputs are conjoint and the sets are disjoint, right? So it's a disjoint, a disjunctive form, canonical disjunctive normal form, not at all simplified. And then what you would use with a karnaugh graph is a Kmap. You would graph this. You'd write create the torus, so to speak, and then you would derive these pieces. The simplification. But obviously, like I said, we can just write a brute force algorithm that just sort of jumps through each piece, starting with the largest sections, and work our way down, and generate each of these. Now this will be the disjunctive normal form, or the sum of products, and we'll just spit out each piece as we go. That's it. I mean, that's as simple as can be. It'll work for all these test cases because these are only 4 variables. So it's 2 raised to the 6th to the 4th is 16. So I think the largest number we end up with is probably this one, which is 24. Right, 4 by 2 by 2 is really 3 factorial, which is 6, and then you end up with just 6 times 4 is 24. So pretty manageable for small numbers of variables, but it gets out of hand pretty quickly. Yeah, I think we'll just end up brute forcing it. I think this is kind of ample territory to write to kind of make better use of the infinite sequences that are available to Clojure, like sort of the lazy sequence evaluation, the infinite sequence manipulation you can do, sort of more proper lambda calculus we can do to get a solution to this, to brute force this. That'll be interesting. I definitely gonna look forward to that. I'm gonna take a quick break, come back, and start to ponder how I might do that. But that's more or less the description of the algorithm. That's kind of like what they're asking, the background information, sort of distilled. Obviously it took me a while to go through all that. I kind of poured over all kinds of stuff to figure out what it was they were trying to explain, trying to get at. Yeah, let me go. I'll be right back. Just take a quick break. Take a quick break. What are these? There it is. There we go. And what do we want to do? Take a break, and yeah, I'll be back. Just mute myself here. Okay. All right. So, whew, yeah. So we're gonna look to code this up now. Code it up shortly. What was I doing? I was thinking, saying, yeah, so it's going to be exhaustive, and we'll do that. We'll perform that. Okay. So let's ponder it. We can start with just setting this up. We can start with that, and that could be good. Get those test cases in there. One should be for this guy. Holy smokes, that's a lot of copy pasting here. Load the test cases to go through. All right, 1, 2, 3, 4, 7, 8, 8 of these. All right, nice. 8 test cases, good. Now, let's go ahead. Okay. All right. Oh, no, no, no. No, not that one either. Okay. Get rid of the rest of these. All right, we can get rid of also the rest of this. Okay. So we want, give us a name, let's say karnaugh maps. So it's interesting, one of my coworkers I was chatting with, and he mentioned that he actually studied under Karnaugh himself. And he was like, Karnaugh, that was my professor. And that was many years ago that he was attending university. And it was also many years ago he was attending university. And like 30 years ago, something like that. And this fellow Karnaugh had invented these Karnaugh graphs already many years ago prior to that. Could find out when it was invented. Is there history? 1953. Yeah. he's 95, the fellow. Holy smokes. Amazing. Amazing. New York City. Oh. So, 1924, he was born, invented in 1953. That would be 29 he was when he invented it. It's pretty good. It's pretty good. Anyway, so also the Veach part is sometimes called karnaugh-Veach graphs, not just karnaugh graphs, right? Or refinement of the Veach chart, right? Right. So, what we want to do is going to take a sequence of a set of sets. Goodbye for now. Sorry, I know I'm singing that song. Has no real meaning to me anyway. Has no meaning to me. I don't know why I'm singing it. What do you call these things? Conjunction of disjunctions. It's the disjunction of conjunctions. Disjunctions. Call them. Fair enough. Alright, so given this sequence of disjunctions. Oh, no, these are actually conjunctions. A disjunction of conjunctions. Excuse me. So, oh boy, this is going to be interesting. You've got a whole boatload of these different variations to look at. Now, how do we do that? Goodbye for now. Probably should stop singing that. I don't know where to even begin. I don't know, man. I'm thinking about I could put all of these into a hash map, these values. And I can also, I guess I could get the two different symbols, right? The uppercase, lowercase values. I wonder, kind of curious how easy if I can convert between these two things. Let me see. I want to go from quote A character. No. Int. Symbol to number. It's This is pretty awkward. I gotta manipulate this A, B, C, and D because they're symbols, but there may be like there's no easy way to go from lowercase a through z to uppercase a through z. That's what I'm getting at here. I'm not really even sure how I can like collect the symbols in the first place. That's kind of what I want to do. Either collect the symbols or because the input and the output has symbols, right? And I want to return symbols as well. Could use zeros and ones. I mean, that's fine too. It's just, it's not quite what they're asking for, not quite what we want either. Because these are abstractions, these symbols, they are abstracted inputs, which is a little different from just a raw 0 or 1. Even though this technically does end up being sort of as you could just call these zeros and ones. No, not really. No, it doesn't really make sense. You kind of want the symbols themselves. I guess if you employ a don't care, no, it doesn't really make sense. It's like the things that are missing are not relevant. It's really the way to think about it. That makes it like a proper simplification. Otherwise, you could do something like 0, 1, x, you know, and have like x's, zeros and ones represent if it's uppercase or lowercase, true, false, and the x's would be like, you know, could be whatever. But the problem with that approach is like you end up with the same thing anyway, right? Like it doesn't really make a lot of sense. I'm trying to reduce the symbolic meaning of these things, this conjunctive form, or rather this disjunction. Trying to combine this disjunction to a smaller disjunction. Interesting. Goodbye for now. Yeah, I should stop singing that. I don't know, man. How do we gather the symbols that we want? It's kind of a somewhat badly formulated question because what's going on? My dad sounds like he's gonna come say hi to me. Okay. It's not clear. It's not clear how to derive Like even part of the problem that's kind of somewhat badly formulated, because in theory you could have any number of variables that you want to use, and also you could have any number of not just variables, but what do they call that? Any number of, yeah, I guess any number of variables, also any number of sets, right? So you could have all zeros, in which case this would be an empty set, but you don't know how many variables it would be, in which case if it's all zeros, then there's no solution that gives you true. So you would end up with, actually I guess you could just end up with an empty set again. This doesn't really matter. Huh. It's confusing because then it seems like any combination works, which is not correct at all. Yeah, the empty set seems to represent that everything is true. It doesn't matter which product you take. But if everything is false, it still doesn't matter which you take, but it should always give you false. Goodbye for now. It's kind of has a funky definition when you're dealing with the extremes. Doesn't quite seem right. Actually, any way you cut it. Like, I don't know what the Karnaugh map looks like or what the simplification looks like if it's all zeros. I guess it's just zero, just empty, just false, you know? If it's all zeros, then you don't even have, because this is a disjunction, right? So it's a disjunction of conjunctions. So you have a sum. So you just have a zero, I think. This is empty. Interesting. And then this would just be zero. Huh. I don't know what to make of all that. I don't know what to make of that. I guess we just won't worry about the empty case because we don't need to consider it here, so we won't cover it. Anyway, so the general case is, yeah, but I'm still stuck on this problem of how do I gather the symbols? How do I get, in other words, I want to get the A's, I want to get the capital A, lowercase a, capital B, lowercase b. I want to associate those things with the zeros and ones, I guess, right? Because I'm going to try to permute through these different possibilities, these different groupings, or generate these different groupings, and try to match each grouping to the set of, try to match each grouping to the set, starting with the larger groupings, working down towards the smaller groupings, and generate each of these pieces as we go. And obviously once you match a larger grouping, you remove those from the set of things to consider. So you have kind of like an iteration, I guess. Loop through this. Excuse me. A reduction doesn't necessarily need to be a loop itself. Hmm. Problem is we need to generate these groupings, and we also need to have a I should have a way to check that all the elements of a particular grouping are present. But that's pretty easy. But generating the groupings is kind of tricky. There's also a tricky thing of like I said, gathering all the symbols that we're going to be using to generate these groupings. Because I think I could just generate the groupings directly, sort of. Thinking about this here. Thinking about this. You know what I can do? It's kind of bad though. I could just define this to only work on 26 characters, 26 symbols, and just take the count of the first set and go from there and generate the symbols based on the count. Right, so if there's 4 symbols, we know it's going to be little a, big A, little b, big B, little c, big C, little d, big D. And that'll be sufficient for these cases also. I mean, I probably don't have to go further than that. If the use case required more than that, then I guess I would code for more than that, but I guess this is simple enough. There is such a thing, I saw another programmer talking about this, of trying to code for the most general case. Like, it's one thing to try to make your code generalizable. It's another thing to code it in such a way that it's like infinitely generalizable to the point where it's just kind of madness and you just never get anything done. I kind of fell into that a while back. I was working on this like sort of Python script to trade Bitcoin, and I was like, all right, everything I do needs logging, and then I was like, all right, I need logging for my logging, and it was just kind of ridiculous. It was fun, but turns out it actually would have been kind of neat to actually execute the thing, but it turns out it was and yeah, I was like trying to add different configurations, and I wrote my own, I think, configuration file, and there was all these like details, and it occurred to me that like there wasn't enough volume in terms of Bitcoin for me to actually make any money. So I was making a few bucks each day, but yeah, not really enough volume to make like real serious money, and so I figured, nah, to heck with it. Although it's kind of funny because since then I lost a lot trying to trade real stocks, and I did fine with the Bitcoin, which is kind of ironic because it's like you'd think Bitcoin being horrendously volatile would mean that you make like you would do better with or rather you wouldn't do as well, but the reason is because I wasn't using derivatives, which have a time span. And the issue with derivatives having a time span is that you can kind of screw yourself. Like, you basically could always just wait for the price to come back to where it should be, and then get back out and get your money back. But if you buy derivatives, then you just lose your money. It always goes to zero at some point, whatever you're trading. So, yeah, it's bad. It's bad. Yeah, definitely say derivatives are probably real dangerous as far as like trading. Kind of bad of me to be as risky as I was with so much money with derivatives, but I got pretty unlucky, I'd say. I mean, it was really unlucky what happened past few weeks, I'd say. So anyway, back to what I was doing. All right. Yeah, we can write something that gets the just do a small check here. If empty, turn 0. Otherwise, continue. And probably use a let, more likely than not. And then we'll say, if it's empty, can do these things. What else? If oh man. If it's empty, return 0. If it's not empty, then we want to get the count of the first. Actually, another if. That's more what we're after here. Count of the first of these conjunctions. If that exceeds, we'll just say 26. And we'll throw an exception. Now, is it dot exception or just exception? That's the question. Exception dot, okay. Kind of unusual, but all right. Too many symbols. Please, something more general. Something else. The thing about exceptions and alerts and things like that, I would like to make them somewhat actionable. So, it's pretty funny. Please ask the author for an upgrade. Politely ask the author for an upgrade. And all right, so we're getting the meat of the program. Say otherwise. So what we're going to want to do is get num symbols, which is exactly this. Right, and then we're going to say, now I do want to try something here. If we, I'm curious if I can produce a list of symbols, lowercase symbols and uppercase symbols here. Quote to, I don't know. Really? I think quote's a macro, that's why. Yeah, I don't think we can map. Okay. Alright, I think we're back. Sorry about that. So, shucks, man. Macro expand quote. Really? Oh, I think I know what the problem is. It's var, not quote. It's quote syn. Oh, really? Alright, I'm gonna have to take a look. No, it's quote. It's a special form. It's not just a macro, right? Jeez, man. "2012, 7 years ago." Man. Quote A. A is quote A. Macro expand. I don't know, man. I don't know. Jeez. So let's try I want to get symbols, right? A list of symbols. I don't know, man. I don't know. What if we get sim of A? Can we do strings to symbols? Clojure characters to symbols. Is there a way to perform this mapping? Symbols. Symbol. Okay. So we can map symbol to a boatload of things here. Error printing. Return value. Sequence. That's what I was looking for. Okay. All right. Interesting that this doesn't work though. So we can take string, and symbol. Ooh. Uh-huh. Okay. Map string, map symbol. I mean, fair enough. So we can do range, character, or even integer to character, Clojure. Where's the character? So you can do character of X. So you can say character of range, let's say take 10 from range, map character. Uh-huh. Range beginning at int of, I guess it'd be A. Uh-huh. Well then. No, we want this to begin. How do we do that again? I mean, you can do could drop the first A of the range also. There's a few ways to do this. I don't think dropping the first few elements is really the right idea though. Range Clojure. Start and step. Can we specify infinity as the endpoint? We can do that. Drop. Yeah, I mean, alright. I was thinking we could use drop. Drop seems kind of not quite what I want. Sure, okay. Use drop then. Save range. Drop. Int of a range. Alright. Nice. Drop one. Okay, so now what we can do is say take map character take, I don't know, 26 map character here. Aha. Aha. Oh. Okay, you can probably see where I'm going with this. Right, this drops to 0, so it is. We don't need the decrement in there. So what I want to do is range drop into A. Take 26 and then map the character. All right. And now we could take that and add one more, which is map capitalize. Nice. Or alternatively uppercase. Upper dash case. Nice. Clojure.string. This is also alternatively there's a few ways to do this one, but you could do this too. Yeah, you do both. Lowercase a, uppercase a. However you'd like to do it. And then what you can do is, depending on this number of symbols, you can take from the uppercase and the lowercase, and you can get sort of the on or off. Yeah, I think I'll end it there. Come back to this later. Still kind of pondering how I want to brute force through this thing. It seems kind of I don't want to say difficult, or just kind of like, well, I don't know. I guess we'll find out. Seems like there's sort of a lot of twists and turns, maybe, is the way to express it. Well, we'll take a look. We'll see. I don't know. I'm not sure. Come back to this. So, yeah, thank you for watching, and I'll talk to you all soon. Have a good rest of your day. Take care. Take care.